In terms of introducing myself, as I mentioned, I'm from the Geography Department. I'm currently the head of the Department of Geography at the moment. I've managed to last 1 year, and as you can imagine, things are rather difficult in the university at the moment, so there's a lot of soul searching and so on going on. But professionally, I've been at the University of Canterbury for more than 30 years now, so I'm a fairly old hand here. I'm a meteorological sort of character, a person who deals with the atmosphere, with the weather and the climate. I haven't dabbled a huge amount in climate change, so you won't have seen my name in lights and lots of arguments going on backwards and forwards. Most of the research that I've done is associated with small-scale variations in climate and applications to human activity. So a lot of the work I've been doing is in relation to air pollution dispersion, its impact on people and so on. Also, more recently, just the last 5 or 6 years, we've been looking at identifying good sites for wind farms. And then, as I'll give you a case study this evening, I'm currently working on a project for the Ministry of Primary Industries on ensuring that the viticulture industry, or the wine industry of New Zealand, is sustainable into the future. And that's using a knowledge of small-scale variations in climate. So I'll give you a little sample of the sort of work we're currently doing. So that's basically about me. The format of the evening is that I'll talk for about 50 minutes or so, and then I'll give you opportunity to ask questions, and hopefully you'll have a few curly questions for me to answer. And also, don't forget that this is a series of what-if presentations. The next one next week is what if New Zealand hadn't fought in the First World War, which sounds an interesting topic to me. So certainly you'll be very welcome to come along, and I encourage you to do so next week. Okay, so let's get into the topic. And as I mentioned, I'm not one of the climate change sort of researchers who you see quite frequently in the newspaper, on TV and so on. I'm a person who tends to be involved with trying to solve practical problems. And the work that I'm going to show you relates to my attempt to understand climate variability in New Zealand's vineyard regions, because it's very important, not just for the quality of the wine that we drink, but also for the exports that we send to other parts of the world. Now, if I can just get this working. Okay, so that was my little introduction, but let's have a look at the summer. So one of the stimuli for this talk was basically people were contacting me and saying, well, what's going on? Why are we getting this sort of weather over the summer? Why are we getting droughts over much of the country? And particularly in the North Island. And you can see from these are sorts of images you can download from the internet, sort of images you see on TV and also in the newspapers and so on. Very unhappy looking farmers in different parts of the country, and obviously unhappy looking cows as well. It says cows without much to eat. As you can see, it's almost completely brown and most of the green grass is gone. So over the summer we had very dry conditions. So what I'm going to do is first of all start with a summary of the summer that NIWA put out, which has a number of things in it that I'm going to emphasize as we go through the talk. You can see for a start, they say very dry for the North Island and an extremely sunny summer across the country. But clearly there are certain regions that were affected more than others. So parts of Northland, North Auckland, the Bay of Plenty, Hawke's Bay and Wairarapa only received about 1/3 of their normal summer rainfall. Also, it was rather dry for Westland and Canterbury, so further south. We were also dry, and even on the west coast, as you probably were aware of from the media. But in some areas you can see it was actually wetter, slightly wetter for Marlborough and the Kaikoura coast, and also around Mount Cook. So there's quite a bit of local variability. Notice also that they indicate, regarding sunshine, high sunshine for regions south of Hamilton. Well, that's most of the country. We ignore Auckland. Most regions experience now this. If we've got record high sunshine hours, why are we getting near average summer temperatures? So I want you to remember that for later on when I try to explain the trends that we seem to be experiencing. So although we got record high sunshine, we actually got near average summer temperatures. They weren't really hot. And certainly in Canterbury, it's not the sunshine that frequently elevates the temperature, it's actually the nor'westers that come over the Alps. And it says above average temperatures for many inland and eastern parts of the North Island and some eastern areas of the South Island. In terms of soil moisture, extreme deficits in large parts, particularly of the North Island. So they really didn't get enough rain. So it's a lack of rain that's most important that comes through here, not necessarily particularly high temperatures. So there's lots of sunshine, but not a lot of rain. So there's a number of questions we can ask ourselves. What caused the summer drought? Why do we get this situation? Lots of sunshine. What are the controlling factors of our changing weather patterns? And I'm going to show you that our weather patterns are changing. There is a trend that we can identify in the data. So I've answered that question already. Is it part of a trend? Well, I believe it is part of a trend. Does it fit climate predictions? Now that's a difficult one because again I'm not really into the climate prediction business, but you could make some linkages perhaps to global warming, and I'll put a hypothesis up as we go through. What are the likely impacts on people, businesses and the economy both now and in the future? And I've shown you some nice media images where farmers are clearly suffering. But do they represent the whole of the country? Because think of the tourist industry, they like the sunshine. A lot of people like to go to the beach. And with my project in dealing with the vineyard industry or the wine producing industry, you can imagine that they're actually enjoying that. They've enjoyed the weather. They've had ripening of the grapes and so on, and they've had a good harvest. In fact, they don't like this weather right now because they're finishing off the harvesting at the moment in Marlborough. So it affects different people in different ways depending on who they are and what their business is. So we'll have a little bit of a conversation about that. The official explanation or summary of last summer's weather, which was released fairly recently, summer was characterised by much higher pressures than normal over the Tasman Sea and New Zealand region, with more southwesterly airflow than normal over the country. So there's a couple of things there. We've got higher pressures, and we'll talk about why that's important. And secondly, we've got the southwesterly airflow. And as you probably know, anybody living in Canterbury, whenever you get a southwesterly coming through, it's actually relatively cool. And that partly explains why with lots more sunshine, we didn't actually get higher temperatures because the wind was coming from the southwest. Okay, so the frequent highs over the country produced a very sunny summer for most of the country and extremely dry conditions over most of the North Island. So let's have a look at that in terms of how weather works in our region, in the New Zealand region. So this is Weather 101, sort of things that I teach my students. Here's a high pressure system, there's a low pressure system. And in our part of the globe, we get alternations between high pressure and low pressure. This is typical for New Zealand. We're not in the tropics where they get the same old weather day after day after day. And we're not down in the polar regions near the South Pole, where again, things are much more constant. We're in part of the world where change is the norm, where we get lots of rapid changes as these weather systems, these lows over here and these highs, move from west to east across our region. And hopefully you're all familiar with the way that happens. And on TV every night, Jim and Karen and all the other weather forecasters tell us about the highs and the lows and the way they move. And generally, we expect them to move from west to east across our region. And in doing so, you can see the circulation around this anticyclone here provides southerly winds in this part and northerly winds over here. And similarly, this low pressure system here has circulation in a clockwise direction around its center, with again southerly winds here and more northerly winds on its other side. And the whole role of these weather systems is to exchange basically air masses of different temperatures. So we've got all those hot air masses in the subtropics and the tropical regions, and we've got those cold air masses down in the polar regions. Now, if without these weather systems, the tropics would get hotter and hotter, and the poles would get colder and colder. And to try and equalize and transfer the energy from the tropical region to the pole, we have these sorts of weather systems. And we just happen to be in the wrong place because we're in where most of the traffic takes place. So that's why we get rapid changes in temperature, rapid changes in weather. So that's how our weather systems generally work. If we average those weather systems over the winter, we tend to find that there's a region up here where we get highs, high pressure systems. So there's the Pacific Ocean high here, a small high sitting over Australia, and then there's the Indian Ocean one just over on the left-hand side. And then we go further south and we get those low pressure systems that circle around the Antarctic. And in between, we've got a region generally of relatively strong winds. You've all probably heard of the roaring 40s and the furious 50s. This is a region basically between highs up here and lows down here where the winds tend to be strongly from the west. So that's the winter situation, but on a seasonal basis, those highs, as you can see here, move south with the seasons. So they move south in our summer, they move back up north in our winter, and they move south, up and down. And obviously, by moving south in the summer, they basically shunt these systems here further south, and we get less westerlies, and we get less low-pressure systems affecting us. And it's, of course, the low-pressure systems that produce the rain, and these high-pressure systems don't. We do sometimes get lows from up north here. Basically, things like tropical cyclones can impact on us, like the cyclone Bowler and so on of the past that have basically almost run out of steam by the time they hit us, but they can do some damage. And you can see over northern Australia, these low pressure systems here are generated really just by the heating of the ground over northern Australia in the summer. So they get a summer cycle of monsoons basically. Once these low pressure systems develop, they get lots of rising motion, and the wind comes from the north, and they get much more rain. This is their rainy season. Okay, so in our region here, these systems move backwards and forwards between summer and winter. If we look at these high pressure systems, because these are supposed to be the features that dominated over the summer, and they did, and they produced our nice sunny weather. Well, let's have a look at them from the Southern Hemisphere perspective. You can see this is just a count of the number of anticyclones or high pressure systems, and you can see most of them occur in a ring around the South Pole here. Over the pole itself you get basically anomalously high pressure because the continent is so high that if you try and correct pressure down to sea level, which is basically the weather maps you see on TV, they're basically pressure corrected to sea level, you get a permanent high down there, but it's actually artificial, it's not real. But certainly these features are real. You can see there are certain preferred regions like this part off the coast of South America here and off the coast of Africa. These are regions where you get dominant anticyclones. In the southern Indian Ocean, you can see the region actually shifts backwards and forwards between summer and winter. But you can see in terms of our region here, the major change seems to occur between winter, when we don't have many anticyclones, to summer, when you can see that there's a high frequency of them in the Tasman Sea here, and also a slightly higher frequency off to the east of us. So quite clearly, we tend to get more anticyclones in our summertime than we do in wintertime, and that's a natural part of our cycle. So we shouldn't be surprised. And if we have a look at the main weather types, and I've just broken them down here into lows and highs, and then I've also put the frequency of westerly winds across New Zealand. And you can see that highs dominate, particularly in February and March, and then they drop off to a much lower level. So up the side here we've got percentage frequency, so that's 50% of the time, or more than 50% of the time, we've got, in fact every second day obviously, we've got high pressures affecting the country in the summer. And this is a data set from about 1950 up to the present. So this is typically the sort of variation we would expect to see. And then you can see it dramatically drops away by the time we get to May here. And then it fluctuates a little bit through the winter, and then up it comes again in the spring. And the low pressure systems, I'm going to have a glass of water. The low pressure systems that you can see drop off, particularly in late summer here, January, February, March, April, and then start to increase as we go into winter. And the westerlies, and they remain about 30% of the time through the winter period and drop down to about 15% in the summer. So weaker winds from the westerly, more highs. So that's the typical seasonal cycle. So we shouldn't be surprised to see anticyclones dominating in our summer. In terms of the type of weather that they bring, areas of high and low pressure are associated with descending and rising air. And one of the key things to remember is that you only really get any significant rainfall if the air is forced to rise. That's why they get a lot of rainfall on the west coast, because those westerly winds come along, they collide with the mountains, and the mountains lift the air, and basically it's like squeezing water out of a cloth. You get this rain falling out of the air because of the lifting. Well, in the center of a low pressure system, this is the region where you've got the air spinning around towards the center, and then the air up the middle of the low pressure system, it's rising. And that's why we get condensation, we get cloud forming, and significant rain. Alternatively, where we get air descending, these buttons are very close together, where we get air descending, as you can see here, associated with our high pressure system, then any cloud tends to evaporate. Because as you push air down, you're compressing the air and you actually warm it up. It's like pumping up a bicycle tire. You know, you're using a pump to compress air. If you compress it, it heats up. And the opposite basically takes place here. As you push air up, as you know, if you get in an airplane and fly up into the atmosphere, pressure decreases. So as that pressure decreases, so the temperature of that air will drop naturally. So we've got cooling of air and the creation of rainfall with low pressure systems, and highs generally produce sunny weather conditions or clear skies. And here I downloaded this this morning. This was yesterday's weather map. So here's this big low pressure system. The South Island is underneath here somewhere. So you can see associated with it, it's not a nice simple blob. You can see some organization particularly in this region here, where there's the maximum rising motion and cloud development, whereas further away you can see there's not nearly so much rising motion. And in addition to this rising motion associated with the low pressure system, the mountains themselves will enhance that rising motion, so you end up with more rain associated with where the mountains are located. If we look at the other effect, here's the effect of a strong anticyclone, a high pressure system. It's actually a distorted satellite image. There's Tasmania just here, So that's Tasmania. And there's this big hole associated with this very strong anticyclone, 1,040. We don't see many 1,040 anticyclones around, but there's a big one, and you can see when you look down on it from above, it's just a big hole. So you're not going to get any rain out of that, and if you've got one of those parked over your country for several weeks at a time, clearly you're not going to get any rain at all. So if we have a look at a much weaker anticyclone, in this case sitting over the South Island of New Zealand, you can see relatively clear conditions, a little bit of cloud down the south here. You can actually see a little bit of cloud associated with the mountains around here and a little bit off the coast here. So even if you have an anticyclone, it doesn't mean to say you're not going to get any clouds at all. Sometimes, as you can see here, you've got fair weather cumulus forming over the land areas, and that's the upward motion associated with that is produced by the heating of the ground. So during the daytime, the sun heats the slopes, heats the paddocks, heats the forest areas, the darker areas particularly, generates warm air, and then the warm air goes up like a hot air balloon. And then when it gets high enough in the atmosphere, it starts to condense to produce cloud. So this is fair weather cumulus here, and some of this will be associated with that type of activity as well. And some of you may have noticed that during the summer, when they were talking about these anticyclones and the droughts in the North Island and so on, along the Canterbury coast, that some days were actually quite gloomy. We actually got a thin layer of cloud, and that is called anticyclonic gloom. That's the technical term for it. When, although you may have large-scale subsidence, although the air above might be descending, you might have something near the surface. It might be the foothills just pushing the air up. It might be the heating of the slopes and so on. So you get bubbles of air detaching from the ground here, rising upwards, and then they meet this large blob of air pushing down, and they've got nowhere to go. So the air goes up, basically like hits a roof, flattens out, and you end up with a sheet of cloud over Canterbury, and it's quite a common phenomenon. And so those are gloomy days when all you need to go is up to Mount Hutt, and you'd be above the cloud, or just flying up through it, and it would be lovely and sunny up above. And also, as I've mentioned, wherever we get mountains, they can produce a small amount of cloud or a larger amount of cloud, depending on how much energy is available in the air that's being lifted up. Okay, so it's not absolutely simple, but basically, generally, with anticyclones, we don't get much rain. You won't get much rain out of these sorts of clouds. You will get some rain out of these. This is the sort of pattern of rainfall development on the west coast, for example. Okay, so people are saying, well, look, what's going on? Is there a trend? Are we getting more anticyclones? Is it getting drier? So as part of this project to examine the climate variability in the vineyards of New Zealand, we started looking at the temperature variations in Marlborough, because Marlborough is by far the most significant wine-producing area. And we started to see some interesting trends there. And so it got me thinking about, why are we getting temperature trends in Marlborough that seem to be a little different from some other parts of the country? And so I started having a look at the frequency of lows and highs over the last several decades to see if there was a trend. And surprisingly, I discovered that there was one. Also, have the westerly winds become more or less frequently? And what's actually controlling our observed changes? And what are the implications for not just the wine-producing parts of the country, but other parts of the country as well? So let's have a look at some of the data. So I plotted up from a classification, a twice-daily classification of weather maps over New Zealand that a guy called John Kidson developed in 2000, but it's being continued right through to the present by one of my colleagues at the Victoria University of Wellington. And he gave me this data set, and I just plotted it up just to see, if there were any trends or not. and I don't think anybody had done this before. And we put all the lows and the troughs together. So these are the features that produce the rain, the cloud and the rain. And you can see that there seems to be a descending trend, a declining trend in lows and troughs from about 40% of the time down to about 36%. So about 4% drop in the frequency of the features that actually produce rain. You'll see there's also an increase in the numbers of westerlies that occur from about just above 20%, about 23% there, up to about 27 or 28% in 2010. So there's something happening that is having an impact on both the lows and the troughs and the westerlies. And when you look also at the high pressure systems, you'll see that they're moving also in an increasing trend from just below 50% of the time, something like 53 or 54%. So it's not a huge change, and there's quite a lot of variation. You can see from one year to the next. You can see a period here when there seem to be lots of high pressure systems, around about 1998 to 2000 here. Then there's a drop off here, and now we've picked up again over the last few years. So we've got a trend, we've got some variations on that trend. Now, I submitted a paper to an international journal and with this information in it to explain the variations in temperature that I observed at Blenheim in Marlborough. And one of the reviewers came back and said, well, that's all very interesting, but why can't you tell us why this is happening, how this fits into the bigger picture? So, which was a good question, because it then led me on to, okay, well, we'll try and explain why these things are happening in relation to hemispheric scale changes in the atmosphere. So I then went back to have a look at these patterns, the patterns of circulation around the Southern Hemisphere, and came across some work that people had done on identifying what is called the Southern Annular Mode, which represents the north-south movement of the westerly wind belt. That's the wind belt just to the south of New Zealand here. And basically they've developed an index that quantifies the northward and southward drift of that westerly wind belt. And the only way it can do that is because the highs and lows are also moving north and south. And so they produced this index called SAM, the Southern Annular Mode, and when it's positive, the zone of strong westerlies moves towards the pole, and when it's negative, it moves away. So it's a measure of the southward and northward movement of these major pressure systems that are so important for our weather. So I thought, well, I'll plot that up and see what that looks like. And look at that. So what it's telling us is that since about 1964, there's been quite a significant increase in the southward shift of all of those climate zones towards the pole. Basically, they're all contracting towards the pole. So the anticyclones are moving south, the westerlies are moving south, and those lows to the south of us, we're seeing less of them because they're shifting towards the pole. So that started to build up quite a nice picture. And so quite clearly, one of the reasons we're getting more anticyclones is that the whole of the Southern Hemisphere is getting anticyclones drifting further south. And then when I plotted just a simple scatter plot between the Southern Annular Mode, so this is more southward down here, and the frequency of these troughs and lows, you can see there's as the Southern Annular Mode becomes more positive, we get fewer lows and troughs over New Zealand, and we get more highs and ridges over New Zealand. So we can show statistically there is a relationship, it exists, and from year to year we seem to be shifting our climate regime. So something is actually going on. Okay, so then we get back to things like global warming and so on. Again, not something that I've spent a lot of time doing research on. But thinking about why some of these, again, this is a very schematic diagram. It just shows you where the major features are. Across the middle here, we've got the intertropical convergence zone centered in the tropics. We've got the trade winds either side. Here's our subtropical high pressure belts in the southern hemisphere and also in the northern hemisphere. There are the mid-latitude westerlies, and there's the subantarctic trough where those low pressure systems move from west to east off the coast of Antarctica. So if these zones are all moving southwards, why would they do that? And I suppose one possibility might be that if the globe is warming up, say we do have global warming perhaps, then maybe the region that gets most of the energy, that's this region here in the tropics, is becoming much more energetic. So these circulation systems here, the Hadley cells we call them, are becoming much more energetic. They're becoming bigger and expanding and basically pushing these other circulation features further away from the equator. Okay, so there's a hypothesis. I don't know if I'm the person to go out and test it, but it's there just as an idea. But certainly something is creating a trend that involves this shift in circulation. So when we come back to the New Zealand pattern, clearly if everything's shifting further south, then these high pressure systems are going to come further south. We're going to get less of these fronts that affect us in the South Island. We're going to get fewer of these lows that sometimes move across us as well. We may, however, get more tropical cyclones shifting our way. Tropical cyclones, though, can only maintain their momentum if the sea surface temperature remains above 26 degrees. So, and generally, the ocean responds much more slowly to changes in climate than the atmosphere. So it may well be that we won't be affected by tropical cyclones for quite some time until the ocean has managed to catch up with the atmosphere in terms of temperatures. But certainly that is a possibility that we may end up. Australia may end up with a lot more tropical cyclones, and we may end up with some that then break loose and head down towards our part of the world. Okay, but is it that simple? Well, I mentioned before that not only have we got more anticyclones, we've also had more southwesterlies. This is what NIWA is telling us, that over this last summer we had more highs, but we also had more southwesterly winds. And that's what I think is happening in terms of why our average temperatures didn't go up. Although we had more sun, we didn't get hotter temperatures. And I came across some other work that relied on an index, or basically produced an index, which is a difference in pressure east-west across our region between Hobart and the Chatham Islands, and uses that index as a measure of northerly and southerly flow. Because if we end up with a low pressure over here and a high pressure over there, then we're going to get clockwise circulation here, and that will enhance southerly flow. But if it's the other way around, if this is high pressure here and low pressure over there, then we tend to get more northerly flow. So if we take daily values of pressure difference between these two sites and average them over a whole year, we get an indication of whether that year is particularly northerly or particularly southerly. Okay? And we can then plot that up. And you can see, again, since 1960 to the present, we've had a more southerly tendency across New Zealand over this same time period. Okay, so it's becoming a bit complicated. We've got more anticyclones, but we've got more southerly and westerly flow, more sou'westers. So how does that fit with the overall picture? Well, it looks something like this. As the NIWA summary indicated, we seem to be getting more anticyclones that happen to be located about here in the Tasman Sea. Now again, remember that these are circulation systems. They're like safety valves that let off steam from the subtropics by transporting warm air, that's this red arrow, from the tropics towards the pole, and exchanging cold air in the opposite direction on this side of them. So here we have a large feature which is basically, its whole role in life is to transport warm and cold air to and from the tropics and the poles. So you can imagine if we get lots of high pressure systems that dominate in this region here, then the flow pattern over much of New Zealand is going to be southwesterly, as indicated by that arrow there. But you can see that then explains why different parts of the world, through changes in atmospheric circulation, changes in climate, different parts of the world respond in different ways. So while we get cooler air masses here, you can see our friends over here are going to get warmer air masses. And as you're probably aware, just over the last few years, they've had record high temperatures. So once these systems get locked into place, you can see that they will produce anomalous situations that, in this case, are basically counteracting each other. So warmer conditions here, cooler conditions over us. But at the same time, because it happens to be a high pressure system, we get more sunshine, but the temperature doesn't necessarily go up. Okay, so what are the implications for human activity? Well, we've already talked about drier conditions, particularly for pastoral farming. A lot of the dairy industry, as we know in Canterbury here, are largely immune because they get their water from the mountains over there and they pipe it in, and they don't need to worry about rain anymore because they just produce their own rain. So in terms of the dairy industry, many of the players in the dairy industry are less affected, unless, of course, these droughts become so severe that they completely run out of water. Better weather for vineyards. It's been a great year for Pinot Noir, so make a note of that. Good vintage this year. Increased fire risk. I don't know if you've noticed that there's been a few more fires this summer than typically. Canterbury and the east coast of the South Island is particularly prone to fire-type weather, and particularly once that nor'wester comes in. But if we're not getting so many nor'westers, which we haven't had too many the last few months, then that's one risk factor we don't have to contend with. But basically, once things get very, very dry, fire is definitely a risk. On the other hand, nicer weather for tourists and holidaymakers. Much more reliable weather conditions when you go on holiday. If there's going to be less wind because we've got these big anticyclones sitting around, then there'll be less wind energy available, and maybe we should be installing photovoltaic panels on our roofs to collect the energy from the sun. And of course, things like faster snow and ice melt. Because if you get a lot of sunshine over the Southern Alps, those glaciers higher up in the Alps are largely affected by the amount of solar radiation they receive, particularly in the summertime, and that affects the snow, the melt rate, and how much water comes out. And of course, I suppose if there's a lot more ice melt, then that's good for farming, particularly those people who use irrigation. So there's all sorts of complicated pluses and minuses associated with the impact of these changing weather patterns. Now I'm just going to give you a sample of the Vineyard case study. We've got this project which basically aims to provide detailed knowledge of local climate in New Zealand's vineyard regions to help the wine industry adapt to climate variability and change. Now, those of you who have visited Europe, you'll notice that they've had hundreds of years to adapt to their local climate when it comes to producing good wine. And so you see the vineyards on the slopes of the Rhine Valley and the Loire Valley and places like that. They've found the niche areas, or at least they thought they had, because the climate's now changing. And so now the French are particularly worried about climate variability, the fact that it's warming up in Europe at a great rate. And so in 2010, I was invited by a group of French researchers to join them and basically take a global perspective of climate variability in the key vineyard regions of the world. And I spent 2 months over there in 2011, and I'm going for another month in June, just coming up, to work with them. But they're extremely worried because they soon won't be able to produce champagne in Champagne. Now, you know how protective they are of their labels, Champagne. But if they can't produce champagne, and nobody else can because they won't allow us to, we'll run out of champagne. And they're so concerned about it, they're actually buying up parts of England. Now, the French buying up parts of England, it's almost unheard of. But parts of Kent have very similar soils, similar topography, and so on, and they're buying up parts of Kent as we speak. And you'll probably notice, too, that they're actually buying up part of New Zealand. New Zealand's biggest wine-producing company, Pernod Ricard, is a French company. And Rothschilds bought a vineyard last year in Marlborough. So they're putting their thinking caps on and thinking like rats leaving a sinking ship. You know, they're thinking, well, if we can't produce it here, we've got to go and produce it somewhere. So they're looking at other parts of the world. But because wine the grape is so sensitive to its environment, so that the aromatic juices that you get from the grape are very sensitive to changes, particularly in temperature, but also soil characteristics and so on. So unlike, you know, growing potatoes or sweet corn or something like that, it's very important whether you pick that terrace or that slope or some other slope, and it affects the quality of the wine that you produce. And for some reason or other, it turns out that Marlborough is extremely good, the best place in the world to produce Sauvignon Blanc at the moment. So we want to keep it that way, and there are various things you can do because one way of assessing a wine-producing region is to look at its robustness. If you look at the microclimates across a region at high resolution, just a few 100-meter resolution, you can identify all the little niche areas for growing Chardonnay or Pinot Noir, Pinot Gris, Sauvignon Blanc, and so on in your region. And then you can project the temperatures to, you know, maybe warm them by 0.5 degree. And then you can identify, you know, what other areas can you use, should you be looking at? And what impact, as a small change in temperature, going to have an effect on where you're currently growing your particular grape varieties and the quality of the wine that you produce. So we're having to look at things at the micro scale, but as you can see, I started by trying to establish, well, what sort of climate variation are we getting in that region, and ended up actually going to a much larger scale. But now we're zooming back down to the small scale to provide them with adaptation strategies so they can grow the correct varieties in different places. So this involves working with plant and food research experts who understand the plant response to their environment. Our group is mostly focused on understanding the processes, the climate processes that occur at that small scale. But when we have a look at these larger scale changes in climate, especially temperature, because temperature is the key factor when it comes to producing good quality wine. I started by looking at the mean annual temperature for New Zealand. You can see there's an increasing trend with some major blips in it. You could probably guess what that blip was at 1991. Pinatubo, the volcanic eruption, cast a veil around the whole globe, temperature dropped, and you can see it persisted for a few years, but also during this period we had an El Nino situation which also cooled the temperatures as well, so it was a sort of a double whammy. And that would be another El Nino in here. and that's a La Nina, and so is that one. So most of the fluctuations we have in temperature, the annual temperature of New Zealand, are caused by El Nino Southern Oscillation fluctuations, which I won't go into, but you've probably heard about them in the media. But overall, you can see that based on NIWA's data from 7 selected sites, there's an increasing trend in temperature, about 1 degree per 100 years. When we look at the vineyard region of Marlborough, this is where the airport is, right in the middle there. This is where we've taken a data set from, so it's pretty centrally located. And you can see also that, there's quite large areas, and most of the land area under grapes is actually on the valley floor. Now, those of you who've been to Europe, you'll find that that's rarely the case. Most of them are up on the hillsides and on the terraces and so on. So the people like the French, when I've taken French colleagues there, they sort of scratch their heads and trying to work out why we're growing stuff on the valley floor. And one of the problems is frost. And one of the issues that when you talk to the vineyard owners in this region is that lots of people have been talking to them about global warming, it's all happening, it's going to get warmer, everything's going to be fine, less frost and so on. And they've been scratching their head and saying, why are we getting more frost? And nobody's actually answered them until I started looking at some of this data. So that's what it looks like. As you can see, very, very dry. As dry as any of those photos from the central North Island. It gets dry every year like that on the hillsides in and around Marlborough. And of course they use irrigation to irrigate the grapes. So what I did was have a look at the Blenheim Airport data, and I compared it with that national trend. And you can see the mean trend shows virtually nothing. There's the same up fluctuations. See a drop in mean annual temperature around about 1991, increase again, there's the peaks. Peaks and the troughs occur at the same time, but basically no increase in mean temperature at Marlborough. That's the first thing I noticed, and then I looked at the other numbers and noticed that the maximum, these are the mean daily maximum temperatures, seem to be going up, and the mean daily minimum temperatures were going down. So not only was the mean temperature staying the same, but the temperature range on a daily basis was increasing. Now, grapes don't like a lot of variation in temperature. They don't like 30 degrees one minute and then, -2 the next. They like a fairly optimal temperature change. So I thought, well, I'll plot up the data and compare it with other wine-producing areas in New Zealand. So there's Nelson, there's Napier, Christchurch, and Queenstown. And you can see at these other sites, we've got Napier, for example, at the top here, Queenstown at the bottom, Nelson in the middle, and even Christchurch showing a slight increase in maximum temperature. You see, Christchurch has not kept up with the other two. The interesting thing happened when I looked at the minimum temperatures. Christchurch has actually done the same as Blenheim. It's showing a decrease in the minimum temperatures, the mean daily minimum temperature, so that how cool it gets at night. Whereas these other sites have all shown an increase. So we've got mean temperatures increasing at these other vineyard regions, except for the most important one in New Zealand, is showing a much greater range in temperature. So I thought, well, if they're getting if we're getting lower minimum temperatures on a daily basis, then what does that mean for frost? And of course, if you look at both Blenheim and Christchurch, there's an increasing trend in frost. So the vineyard people were right. They are getting more frost. Global warming is happening and they're getting more frost. But at the same time, their maximum temperatures are higher too. So they've really got to adapt to a different sort of climate. And if we just focus on the important frosts, those are the spring and autumn ones at Blenheim Airport, you can see quite a significant increase in the occurrence of those. So the spring ones, if they get a frost and that's not forecast and they don't have any frost protection techniques, it'll wipe out their crop. So it's hundreds of thousands of dollars overnight will just disappear off their balance sheet. So frost is extremely important. But not only that, because of the life cycle of the grape, if you have a damaging frost this year, it doesn't just affect this year, it actually affects the next year as well. Because at the same time as the buds are bursting for this year, the buds for the following year are just being created. So you can have 2 bad years through one major event, and that's why they spend a significant amount of money on helicopters. Sometimes they can have more than 100 helicopters operating in the Marlborough region in the springtime, making all sorts of noise, and of course the locals don't like it very much, unless they're in the wine industry. And so yeah, it's the hazard. One of the key hazards that they have to contend with has actually become worse. And the interesting thing is that having got that data together, I thought, well, I wonder if anybody else has discovered this. And I was poking around, and somebody actually pointed me at this report here. And then I noticed that one of the authors was called J. Sturman. And blow me down, it was my son. And he never bothered to tell me that he'd written this report. He works at NIWA in 2009, and here we are in 2011. He never bothered to tell me. He knew I was working on this sort of stuff, and so I had to give him a hard word. But the work that they did illustrates that different parts of the country have experienced different sorts of trends. This is 1972 to 2008, screen frost minimum temperature. So that's the temperature below 0 degrees. And you can see in the color code here, that's 0, no change. Red means, I think that doesn't, I'm not sure how real that is because it's all up in the mountains. But when you come down to the coastline here, there's actually been an increase in the frequency of frost in this part of the country, in Canterbury, so that fits in with the Christchurch data. You can see that they've just got a little blue patch in Marlborough, so there's some suggestion that it may be spatially variable within that area, and we need to understand that, how the vineyards nearer the sea and further to the sea may or may not be affected. The Marlborough region, you can see here, and then in the Wairarapa, Martinborough area where they produce good wine, and also extending into the southern parts of Hawke's Bay here. And other parts, you see, have actually experienced a decrease in the number of frost. So it's a lot more complicated. So the message, one of the key messages I want you to take away from here is that when you hear people talking about global warming and temperatures going up, well, it may be in some places, but in other places, we've talked about Australia versus New Zealand. Now we've come down to a smaller scale. We've got the East Coast versus the West Coast. We've got the North Island versus the South Island and so on. So it's not going to be the same for everyone. And different parts of the country will be impacted in different ways as the climate changes. And climate change is a natural process. So in terms of one of the things that we notice, this large area here, particularly along the east coast, seems to indicate a certain amount of cooling and increase in frequency of frost. So when we look at the trends in the Marlborough region, the maximum daily temperatures have increased, and I've done some more work in basically doing some statistics relating the frequency of anticyclones to temperature changes and so on. And it seems to be the southward shift in anticyclones that has caused this maximum daytime temperature to increase a little. And that's because it's sunnier. You know, you do get a certain amount of daytime heating. But also the minimum daily temperatures have changed. But when I did some statistics, I discovered that it wasn't just the anticyclones. It wasn't those clear skies at night. Because if you get clear skies during the day, you get lots of energy in. But at clear skies at night, all the energy goes out. And that's when you get the frost. But it wasn't just those anticyclones, the clear sky at night effect. It was also the fact that we were getting southerly winds. So the air masses we were getting were cool already. So they didn't need to cool down much more to produce frost. Frosts appear to have increased over recent decades, particularly in Marlborough and other parts of the country as well, in spite of global warming, and particularly in those crucial spring and autumn periods. And again, this relates particularly to those clear and cool nights that we're experiencing. And the mean daily temperatures have tended to remain relatively constant, in contrast to that national temperature trend. And again, this appears to be due to the counteracting effect of the warmer days and the cooler nights. And again, the cooler air masses that we're getting from the southwest are partly to do with that. And of course, the exposure to those air masses is most important. And up the east coast of the South Island, it's not surprising that we would feel this effect most because we're more exposed to those south and southwesterly flows. So in just summarizing my talk today, first of all, we have to remember that New Zealand weather is normally variable from both day to day and year to year, and that's going to continue. So we'll get summers like this year, and we'll have summers like last year when it rained every week. So that's normal, but we do have these underlying trends. And these have produced quite significant impacts on our local weather. And as I've indicated there, these are associated with shifts in the atmospheric circulation of the whole of the Southern Hemisphere. So there's a big picture of things happening out there that I don't really understand, and I'm not sure that some of my colleagues overseas understand them yet either. But the main features seem to be moving southwards. Now, they can't keep moving southwards because eventually, I mean, they can't all disappear down the South Pole, as it were. There's no big hole where all these circulation systems disappear. These shifts may or may not be associated with global warming. Now, the implications for New Zealand are more complex than a simple increase in temperature over time, as the weather systems interact with mountainous terrain in a complicated way. So what happens on the east coast and the west coast could be quite different. The impact on human activity, as I've indicated, depends on the type of activity, how much it relies on things like air temperature, sunshine, and those sorts of things, and rainfall, obviously, as well. But clearly, there's likely to be some winners and losers here. So you might want to use this sort of knowledge towards futures trading, for example. You could make money out of this if you really understand what's going on. Now, it just so happened that last week a study came out, I don't know if you heard about it in the newspaper, by Hannah et al. This is a group of researchers in America and in North America and South America in particular. They did an analysis of the whole world. They took the output of 17 of these climate prediction models, which predict the climate by 2050. And they looked at what the temperatures would look like by that time, and then related those temperatures to the different varieties of grapes and wine production in different parts of the world. And in particular, in Europe, obviously, North America, South America, and they also had New Zealand in there as well. And they identified that New Zealand will be the big winner, because parts of the Mediterranean will no longer be able to produce, they'll get too hot for the grapes, and other areas that will benefit will be Northern Europe, and as I mentioned already, they're looking at England, but also Northern Germany, places like Denmark and so on, moving into Scandinavia, and parts of North America. But other parts of North America will also be adversely affected as well. Now what they've done, they've taken a very broad brush analysis. They haven't looked at the Southern Alps and the terrain at that sort of level of detail. They've just looked at a global picture. But on the basis of that global picture, for example, compared to Australia, where the Australians, once the temperature gets so high, it's all off. You know, they need to be looking at Tasmania, and in fact, some of them are, in terms of grape production. But we've got a lot of flexibility because our environment is very complex. There are all sorts of microclimates between Northland all the way down to Bluff. There are all sorts of little microclimates, and if you go down to Otago, you can see where they're growing grapes. I mean, people would say, Otago, it's impossible to produce wine in Otago, but they're producing superb Pinot Noir because they've just found those little terraces, those microclimates. And so this is the sort of thing we need to do, is to look at things at reasonably high resolution and work out if we need to adapt, how we need to adapt. The microclimate at that sort of resolution allows us to grow the right sorts of grapes in the right places, manage the crop in different ways by controlling soil moisture and the canopy of the grapes and things like that. And then also control the pruning process as well, can advance or bring back the date of harvest, for example, those sorts of things. So there's ways in which you can manipulate the crop as well as finding good sites. So what I've tried to do then is just give you an idea of, first of all, what's actually going on, and secondly, how we can use knowledge about what's going on to help us make good decisions about the different sorts of activities that we're involved in. So I'll leave it there. Thank you.